There's going to be a lot of stuff here, but it's going to be great. Okay, so I want to show resonance with the mass spring oscillator, but that means I need to build up a whole bunch of systems. I'm going to do it all in one video. I'm not going to stop. It's going to be as long as it needs to be, and no one's going to stop me. So I want to look at a mass on a spring, and then I want to look at a mass on a spring with a viscous dampening force, and then I want to look at a mass on a spring with a dampening force and a driving force, and then I want to find the resonance of the system. Let's get started. It's going to be great. So we're going to start with the mass on a spring. So that means I need an anchor point. I don't always have to put that, but I'm going to put, there's an anchor there. So there's a point where the spring is attached to. And then I have a spring. I drew that myself. Thank you very much. And then I have a mass. And I need to find the force that this spring exerts on the mass. And I'm going to start with the unstretched length of the spring. So I'm going to call that L0. Then if I stretch that spring, it's going to have a new vector length. Okay, so L0 is a scalar value. That's how long the spring is unstretched. L is the vector from the anchor to the mass, and I'll show you that in a little bit. But if I stretch that spring to the right, then there's going to be a force to the left. The spring's going to pull back to the unstretched length. And we can write an expression for that spring force as the following. So we have negative K, where K is the stiffness of the spring. We call that the spring constant. And then we take the difference between the length of the spring, the magnitude of the length L, and the unstretched length L0. And the difference between those tells us the stretch. Now, in order to make the whole thing a vector, I have to multiply by L hat. That's a unit vector in the direction of L. So that's my force due to the spring. And I have a couple other videos on that, but that's all you need to know for right now. Now, what do we do with this? Okay, so first, let me show you how to get the vector length of the spring, because we actually want to model the motion of the mass based on the force and the position and the momentum. Okay, so let's say I have this spring system right here. I have the anchor at some position RA. So there's my origin down at the bottom of that arrow, and then it points to the location of the anchor. And then I have RM, which is the location of the mass. The difference between these, RM minus RA, would be the position the vector L, the length of the spring. And I'm doing it in this detailed way because later I'm going to make it more complicated. And this way I don't have to have the anchor at the origin, and I can do more things. So it's better. And then so here is that force that I already wrote down. Let's redo that. The other thing I need to deal with is the momentum. So imagine now that this mass is moving to the right and has some momentum vector to the right. What does a force do to momentum? This is the momentum principle. This says that the net force is the change in momentum divided by the change in time. And if the force is not constant, then you'd really have to write this as a derivative, and I'll get into that a little bit, what to do with non-constant forces. But this is if you have a constant force. And I can write the change in momentum as P2 minus P1. So this says that if I take the momentum at the beginning of the time interval P1 and the momentum at the end of the time interval P2, then I can write delta P as that change in momentum. They are vectors though. So I can multiply both sides by delta T, and I flip the sides just to make it easier. And then I can add P1 to both sides. Now here is, there you go. I put that out of order. So I get P2 equals P1 plus F net delta T. That's from the momentum principle. If it is a small time interval, if delta T is very small, then even though the mass is moving and the position changes and the force changes, this is approximately true. So for small delta T, it doesn't matter that I have a changing force. And that's the brilliant thing in a numerical calculation. Okay, I want to update the position. We call this actually the momentum update formula. I want to also update the position, the momentum. No, I just did update the momentum. I want to update the position. But in order to do that, I need the velocity. So just a reminder that the momentum is mass times velocity. Then I can write the average velocity as this. Well, it's obviously P over M. Okay, and I'm going to drop the average because I'm dealing with small time intervals. And that's the change in position over the change in time. So again, I can assume that R1 is the position, and this is the position of the mass, not the anchor. So I dropped the M because, the R1 is the position at the beginning of the time interval. R2 is the position at the end. I can just do the same thing I did before and solve for R2, and I get this. R2 equals R1 plus P over M delta T. Now, I do have a small problem. I'm going to actually let's do the following. This is the order that I'm going to do this numerical calculation. Number one, I'm going to calculate the spring force. And you'll notice that has the vector L in there. And so that does depend on the position of the mass. Number two, I'm going to use that force to update the momentum, which is wrong, right? Because the force changes. But if my time interval is small enough, it works. And then number three, I'm going to use that to update the position. Now, I just updated the momentum, so I'm actually going to use P2 here. I'm going to use the momentum at the end of the time interval to find the new position at the end. And then I can just go back over and start over and do the next time interval and the next and the next and the next. And that's the key to a numerical calculation, which we want to do in Python. So I want to not just calculate this in Python, I want to show it in Python. So here is my Python representation of a spring. So I have the anchor, the yellow dot, I have the mass, the red ball, and I have the spring. I'm going to show you how to draw these in Python. And then we're going to do it. So the first is the anchor is a sphere. So a sphere is an object in GlowScript v Python that does these three-dimensional things for you. So if you're using VPython or GlowScript, I'm going to use GlowScript, which is an online version. If you say sphere, this function sphere, it makes that three-dimensional sphere. I can give it a location of the center of the sphere. That's the value POS for position. I can give it a radius. I can give it a color. So anchor equals sphere, and the position is vector negative L over 0 over 2. So I've said that it's a 20 centimeter long spring. And the anchor is negative L0 over 2 to the left, and the mass is L0 over 2 to the right, just to make it in the middle of the screen. And then I give it a color. And then I do the exact same thing for the mass. It's just a sphere. It's just at a different location, different size, different color. Now I need to do the spring. The spring there's a built-in function in Python called the helix. You could just use a cylinder if you wanted to, because it's just for visual, but I want to make it look nice. So the helix has a couple of important properties. The position is the location of one end of the helix. And then the axis is a vector from that position to the other end of the helix. So that is going to be the difference between the mass and the anchor. So I just take the difference in those positions, and that's going to be the same as the vector L, really. Radius is the thickness of the whole, if it was a cylinder, the thickness of that, and thickness is the thickness of the wire. Okay, I need one more thing. What are my initial values for this? Because if I calculate the updated momentum, I need to know what the initial momentum was. So let's start with a mass of 0.02 kilograms. I already said the natural length, the unstretched length of 0.2 meters. The spring constant 2 newtons per meter. L is the initial position. So I'm going to have it stretched 2 centimeters. And then time, and then I'm going to use time step of 0.1 seconds. I didn't say it here, but I should say it now. The initial momentum of the mass is going to be 0. Okay, and so I'm going to make this, we're going to oscillate it, we're going to make a graph, and then we're going to come back and do the next part, adding the dampening force. So let's skip over to Python. But it's nothing I didn't already show you. So I have the same thing over here, and this is in trinket.io. It's GlowScript Python. You can see it up here, but it has this side window and then a display window over here, which I really kind of like, and you can move this back and forth. Okay, so let's get started and do what we said. The first thing I need to do is to put in all my initial values. So I need to put the mass of the spring. So up here, I'm just going to go down and say mass.m. So if I do that, I'm giving the property m to the object called mass, and I'm going to say 0.02. 0.02. I already have L0. I need the spring constant K equals 2. I need this. I'm going to start off, let's just put this at, this is going to be plus 0.02 for the X location of the mass. So I'm going to stretch a little bit to the side. Let's go down here, let's put down here, T equals 0, dt equals 0.01. 0.01. Okay, I think I have everything. Now I'm just going to make a loop. Okay, so to do those calculations over and over. And let's just say while t is less than 5, I just pick something. Rate 100. So rate 100 says don't do more than 100 calculations per second. And since the mass, I'm doing time steps of 0.01 seconds, this would make it run in real time, if it can run in real time. Next, I want to calculate the force, but in order to do that, I need to calculate L. Okay, so L is going to be equal to mass.pos minus anchor.pos. Because remember in that diagram before, I showed that it was the vector to the mass minus the vector to the anchor, and that'll give me L. Now I can calculate the spring force. Fs equals negative K times the magnitude of L minus L0 times norm L. So mag L is a built-in function in Python that returns the magnitude of a vector. Norm is a built-in function in Python, in GlowScript v Python, that returns the unit vector for a vector. Okay, now I just need to update the momentum. So it's, I didn't put that in here. So let's say mass.p, we're going to use p for momentum, is going to be equal to mass.m times vector 0, 0, 0. So this does a couple things. One, even though it's 0 times a constant, that's fine. But it sets the momentum as a vector quantity, right? I can't update it if I don't know what it is. So it is important to have it at 0. Now I can say mass.p equals mass.p plus fs. Actually, I should call this, let's call this fnet. And let's say fnet equals fs. I know that seems silly now, but trust me, you're going to think, oh, that was a good idea. Good thing you did that. Times the time step dt. Now I need to update the position. Mass.pos equals mass.pos plus mass.p times dt divided by mass.m. Okay, I need to update time. T equals t plus dt. Now I actually do need to do one other thing. I need to update the spring. I need to visually show the spring. I don't need to move the position because that didn't change, although I'm going to put that in here anyway. So I'm going to say spring.pos equals anchor.pos, which it was before, and then spring.axis equals the vector L. No, I'm going to recalculate L. Let's do this. Let's move this up here, and then let's put it again down here. That way it will be the position at the end. So it's just going to be the vector L. Okay, I think we're ready. Let's save it and run it. Nothing happened. K is not a function. You know why? Because I put K in the times. Okay, got it. Check that out. I'm pretty happy. Okay, and it's in 3D. It's coming out at you. Okay, let's do one last thing. I want to make a plot of the total energy. So if I take the system of the, I should have put this in the presentation, a system of the spring plus the mass, then the total energy should be constants. But I want to graph the kinetic energy, the spring potential energy, and the total energy. So let's make a graph. So let's say T graph equals graph. X title is going to be time in seconds. And the Y title, the Y axis is going to be equal to energy in joules. Okay, so now I need three, that just sets up the axis. I need three graphs. So FK is going to be G curve, color equals color dot red, label equals, this is called kinetic. FU is going to be equal to G curve, color equals color dot blue, label equals spring potential US, this is called US, and then FE, F total, is G curve, color equals color dot green, label equals total, E total. Okay, now down here I need to plot these things at the end. So I can say I need to calculate K equals, it's going to be P squared over 2M. So it's going to be mass, mag, mass dot P squared divided by 2 times mass dot M. That's the kinetic energy. The spring potential energy, oh, I need to calculate S, right? Let's just do that. S equals mag L minus L0. Now I can say US. US equals 0.5 times K times S squared. And then E equals K plus US. Now I can plot these. Fk dot plot T K, Fu dot plot T US, and then F total. Did I call it total? I've already forgotten what I called that. Total equals dot plot T E total. Wait, what did I call that? E. Let's call it E. Okay, let's run it. US is not defined. That's why. Oops. T. Oh my gosh, I'm losing it here. Okay, down, 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 down. I thought I hit that. Put 2 equal signs there. Oops, sorry. Oh, US equals. See, I got out of control. Okay. Now you'll notice here, the kinetic and the total energy is not conserved. So this is good, right? So this just says that my time step is not small enough. It's actually not bad. There's a little change in there. It's not bad. Let's just make this a little bit smaller. 0, 1. Let's go down here and increase the rate. Let's do it again. Let's see what happens then. Yeah, now I have energy fairly constant, so I'm pretty happy there. Okay, let's add a dampening force. Okay, so now we want to add this dampening force to it. And this is going to be viscous drag. So imagine like this mass is moving through oil or something like that. And so the mass is moving to the right, so it has momentum to the right. But there's a force pushing in the opposite direction, the viscous force. And in this case, I want to say that this force is proportional to the velocity of the ball. And there's some constant in there that depends on the type of oil that it's in and the size of the ball and stuff like that. So I can calculate the viscous force as just the product of that constant negative, that constant times the velocity. And that'll put it in the opposite direction. So I don't want to use velocity, I want to use momentum because I was using momentum. So I'm going to say negative C momentum divided by mass. Now I have a net force of the spring plus the viscous force. And then I'm going to do my same old thing, calculate, update the momentum, update the position, and then update time. Now, I do need one thing. I'm going to pick, and I think this works, I'm going to use a value for the drag coefficient of 0.3 Newton seconds per meter, and let's just see what happens. So I'm going to add that into my calculation. So let's go back to the program and put that in there. Okay, so here we are. I haven't done anything to the program. It's the same way that I ran it. I'm actually going to change this to... that time's a little bit long. Let's put that 3 seconds. Up here, I'm going to add in that drag coefficient, C equals 0.3. Now, I need to calculate, here I calculate the spring force. I need to also calculate the viscous force. So let's say VFV is negative C times mass dot P divided by mass dot M. That's it. And I'm going to add that in here, FV. Now, it's important to realize, look, these are vectors. Fs is a vector. F spring is a vector. So I don't want to do any kind of subtraction here. I'm adding F net as the sum of the vectors, right? They could have a negative x component. That's fine. But that's in the vector. That's it. I don't have to add anything else. Let's just see what happens. Okay. That's cool. That worked. Okay, I'm going to change the drag coefficient a little bit lower. But you see here that it didn't really oscillate much. It was the viscous force is very high. So let's just decrease the drag coefficient by a factor of 10 to make it a little bit thinner oil. See what happens. Okay. I'm looking more at the graph than the other thing, but it's gonna... That's cool. So you can see that both the kinetic and the spring potential energy died down. It did lose energy because it's losing energy to the oil. So it's interacting. There is work done on it in this case. So that's a pretty good graph. Okay, so we have the dampening down. One thing you can always do is just to check things are working. And also notice I built this mass without the viscous force and got that working first, and then I added the viscous force. I should be able to turn off the viscous drag by just multiplying this by 0, and it should go back the way it was. Let's just double check. Yep. Okay, turn that back off. Okay, now we get to make it a damped driven. I want to drive the thing. And I'm going to do that by moving this anchor point. So let's go back and I'm going to show you how to make this work. Okay, so here is the same picture I had before that shows the location of the anchor and the location of the mass. What I want to do is take that anchor and just move it back and forth. And that will be my driving force. So I need an expression for that. So let's use this. Suppose I have the position of the anchor is the initial position of the anchor, which I already know. That's what I'm going to call that RA0. That's where it starts at. I'm going to add onto that this d sine omega d times t. So that makes it going to oscillate back and forth. This mass is going to oscillate back and forth with an amplitude d. I'm going to use 0.001 meters. I'm going to change that because I don't even know if that's a good value or not. With the frequency omega, that's how fast it's going to oscillate back and forth based on the original position. So I'm going to use omega d as a fraction of the natural frequency of the mass. Okay, so if you let the mass alone, and I have another video that calculates this, the angular frequency angular frequency of the mass by itself would be square root of k over m. So I'm just going to have a little bit smaller than that. Okay, let's add that in there and see what happens. So here's the old dampening program. Let's add in our new constant. So I have d equals 0.001. I need the initial position. So let's call that RA0, just like I did before, and just going to be anchor.pos. That's where it starts. And then I need, let's call this omega f for the spring, the natural spring. This is going to be the square root of k divided by mass.m. And then omega d, the driving frequency, it's going to be 0.9 times that, times omega f. So down here, the first thing I'm going to do is update the position of the anchor. So I'm going to say anchor.pos equals d times sine omega d times t plus RA0. I think this will work. I think that's all I need to do. Let's just see. I feel like something's missing, but let's just run this. Can't add a vector and a scalar. RA0D, oh, that's right, times vector 1, 0, 0. Okay, so it looks a little weird because the thing is zooming in and out. I can't even. I do think it's working because look, this doesn't go all the way down to 0. That I'm pretty pumped up. Okay, let's do up here. Let's see, what was it? Scene dot auto zoom auto scale equals false. Is that true? Maybe not. No. Let's just get rid of that. Don't worry about it. Okay, so now let's make it a little bit higher amplitude. Let's crank this up to 0.5. Okay. Check that out. It's getting more higher amplitude. Oh no, I think it's going to go back down. Let's just run this for longer. Let's see if it goes back down. Because I might have my... Now, it can get at a higher energy than it started with because that driving force is indeed adding energy to the system. So it can go back up. Now it's going back down. Okay, I'm pretty excited with that. Let's just put this driving force as something crazy high. The frequency of right down here. Let's say it's 3.9 times that. Let's just see what happens. Okay, now I said I wanted to do resonance. That was the key, right? So what happens if the frequency of the oscillator is the same frequency as the natural frequency over here? So what if I put this as 1 times that? Now you'll notice that it keeps getting bigger and bigger and bigger and bigger. Let's just even do this. Let's increase the dampening force to 0.1 and run it. So it's still getting a little bit bigger, right? But if I turn that that's a really high dampening force. Let's just go back to a frequency that's off by like 0.8 and then run it with that high dampening force. We could play with this forever, and I think I could, but I'm not. I'm going to try not to. So you see here, it's actually, is it decreasing? I think it might be decreasing. It's pretty close though. Let's decrease this down to 0.7. Let's do 0.5. But I have a fairly high dampening force. Yeah, so now it's just going to stop, right? It doesn't really have enough to get the thing going. But if I decrease the dampening force to 0.01, then you'll get a lot more cool stuff. Okay, there's so much I could do with this. I think I'm going to have to write up something more detailed with everything in here because I could play with this forever. And really what I wanted to do is to make a plot of the average amplitude as a function of the driving frequency to get this resonance curve that you've seen before, but that's going to take a lot more work. This is good enough for me. I think I did indeed build a damp-driven oscillator, and I'll stop here. So I'll include the links to this code down below and a whole bunch of other stuff